Welcome to the Priority Queue Data Structure video. We are Alec Herskowitz and Matt Weber, and this video was produced for CSE274 at Miami University. The priority queue is a simple, abstract data structure. Its purpose mirrors that of the standard queue all data structure students should be comfortable with. A queue is a first-in, first-out container, which means the order in which elements are removed or dequeued is the same as the order in which they were added or enqueued. Queues can hold any type of data, but for the purpose of this video, we're going to assume we're working with integer queues. Here's a quick demonstration of the way standard queues work. Let's start by enqueuing a few elements. And now let's dequeue an element. And you'll see that the 1 is returned to the caller, and the rest of the elements stay in order, ready to be dequeued. Now let's dequeue a few more, and enqueue one more. And as you can see, the queue isn't that complex. Now, a priority queue is also a first-in, first-out container. However, ordering is only guaranteed given the same priority. In the priority queue, unprioritized elements are removed last, after any elements which have been given priority. Depending on the implementation of the queue, you could have discrete levels of priority, such as high, medium, and low, or a continuous scale of priorities. For our purposes, we're going to use a low number base priority, so a 10 is more important than a 50, which is more important than a 100, which is of course more important than any non-prioritized elements. Let's look at an abstract representation of the way a priority queue works. We'll enqueue from the left and dequeue from the right. Now we'll first enqueue a non-prioritized element, and now we'll enqueue another element, this one with a priority of 15 set. Now, the new element gets to jump the original non-prioritized element in line. Let's enqueue another non-prioritized element, and it takes its place at the very end of the queue. Let's enqueue another prioritized element, but with a lower priority than the original. And we can see that it remains behind the higher priority. Now let's dequeue that 5. Now the priority is no longer important, so it's discarded and the 5 is returned to the caller, and the queue shifts. Now let's just add one more element with equal prioritization as the 0, and you can see that the 0 remains in front of the 11 in line. And then we can just continue to dequeue as normal. Once the queue is set up, you dequeue from the front just like a regular queue. So that's about all there is to it. Just remember, first in, first out, given equal priority. Let's take a look at a typical implementation of a priority queue. In general, the most efficient implementation utilizes a heap. The necessary methods for the priority queue structure are enqueue, enqueue with given priority, dequeue, which returns the element, and a Boolean check to see if the queue is empty, as well as the size of the queue. If we hop over and take a look at the implementation of the class, you'll see that we've gone with the C++ standard template library implementation of the heap, so we can focus on the mechanics of the priority queue itself. Upon creation of the empty priority queue, we create an empty node vector, vectors being in essence dynamic arrays, which allows for more efficient swapping of elements than a linked list would provide us. So when we enqueue a non-prioritized element, we create a new node object and push it to the end of the vector, and then use the STL push heap method to ensure our heap structure is maintained. Push heap is big O of log n, which makes our enqueue big O of log n as well. When we enqueue with priority, we do the same, but call a different construction of the node. Looking at the dequeue method, we remove the head of the heap, which is the highest priority element, and then we move that node to the end of the vector and remove it. We then ensure our heap remains ordered, which is a big O of log n operation. Compare this to, say, a linked list implementation where dequeues would occur in O(n) time due to iteration of the entire list to find the highest priority element, and you can see why the heap implementation is preferred. The real magic is happening in the node class. If we create an unprioritized node, we set its priority to be the maximum value of a signed integer. Also, all nodes have a unique age field, which turns out to be very important to ensure that when sorting, the first element added remains in the first position to be dequeued. And the final bit of logic is right here, the less than operator used by the STL heap to ensure ordering. First, we see if two elements have the same priority, then the oldest is considered to be lesser, otherwise the element with a higher priority. So here's a quick test of the implementation. We'll enqueue some integers with various priority and ensure they come out in the right order as predicted here. And it looks good. So now let's look at a few examples of where a priority queue would be used. A real-world example of a simple priority queue is at amusement parks. Most visitors are in an unprioritized queue when waiting to ride an attraction. However, certain guests, such as VIPs and disabled riders, are able to bypass the non-prioritized queue. Another real-life example would be a simplified grocery store with only 2 lanes, one for express shoppers and one for regular. Anyone with less than 12 items is prioritized as they enter the line, and everyone else gets handled in the order that they entered the non-prioritized line. The priority queue has very important uses in computing as well. Anytime we have limited resources available, we need to be able to decide what operations or actions are most important. One application is network traffic shaping, where certain packets need to be prioritized and routed first, such as voice over IP. VoIP is more latency sensitive than, say, BitTorrent, so routers need to prioritize that traffic. So as you can see, priority queues are important and occur all around us. I hope you learned everything you never knew you wanted to know about priority queues, and we hope you enjoyed the video.